The Sun is a giant, bright celestial object of intense nuclear energy. It unleashes billions of tons of electromagnetically charged plasma hurtling into space every day. These violent eruptions, called coronal mass ejections, or CMEs, shoot off into the solar system, causing what we know as solar storms. These highly charged plasma particles race towards Earth at over 1,000,000 kilometers an hour. And one might think that with the speed and intensity of these particles, we should all head for the bunkers when they arrive. However, the Earth has natural protections in place to prevent most of these particles from hitting us. One such protection is the Earth's powerful magnetic field, which pushes the particles around the planet and to its poles. Particles that do hit the atmosphere are absorbed and provide the energy to drive the climate on our planet. In fact, the Sun is crucial to life on Earth. For example, it provides just the right amount of warmth and light so that plants can photosynthesize the Sun's energy to usable carbohydrates. This energy makes its way down the food chain until it reaches us, humans. We eat and convert food to give us energy that our bodies can use. Almost all food energy can be traced back to the Sun, our life giver, and the very beginning of our food chain. But could the solar system's giant also create catastrophe? How big can these CMEs get? What if the largest solar storm of all time was to hit Earth tomorrow? Could the Sun actually damage or destroy humanity? For a star, our Sun is relatively stable, a type of star informally known as a yellow dwarf. It is middle-aged and has not changed dramatically for the last 4 billion years. We can be glad our Sun is as stable as it is, as unlike most other stars, the energy it emits is fairly constant. If you were to look at footage of the Sun taken by the Solar Dynamics Observatory, however, you would quickly realize that even one of the most stable types of star has a landscape of activity. Sunspots, solar flares, and coronal loops are present every single day on the Sun's surface. Could say the surface almost appears to be fluid, but the Sun is neither solid, liquid, or gas. It is rather a giant, nearly perfect sphere of plasma. It is composed of mainly hydrogen and helium, and at the center of the Sun, due to its enormous mass, nuclear fusion takes place. At the Sun's core, hydrogen atoms are fused together under immense pressure to become helium.
The Sun itself, I tend to think of it as an onion. It's really consisting of different layers. So in the core, the very center of the Sun, essentially that's where nuclear fusion happens. Now you have to think, so essentially the Sun is kind of a huge ball of plasma, soup of particles, ions, atoms, electrons, sort of everything mixed up together. On average, it takes a photon to travel through the radiator zone something like 170,000 years. It's basically it's that dense.
And then from that, it then hits the convective zone. So everybody knows that hot air rises and cold air falls. So what then happens is the material is very hot at the bottom near that radiative zone, and then it expands and it rises to the surface, and that's the main transfer of heat from that point onwards. Obviously then glowing from the surface like any hotter material does.
Plasma is an extremely good conductor of electricity and is also affected strongly by magnetic fields.
So sunspots are actually the surface representation of the magnetic fields of the sun. So the magnetic fields actually get very tangled below the surface. So between that radiative zone and the convective zone, the magnetic fields get tangled.
They tend to appear in pairs, in groups. I mean, if you think sort of a magnet, you have positive polarity, negative polarity. I mean, that's sort of normally what we see in sort of in sunspot pair. You know, one would be positive, the other would be negative. So and normally sort of the strongest magnetic fields that we observe are in the sunspots.
The sunspots can be anywhere from about 15 kilometers in size to around about 160,000 kilometers, so multiple times the size of the Earth.
Sunspots can often be seen at the base of various solar phenomena. Coronal loops, large rings in the sun's atmosphere, prominences, large, bright, gaseous features extending outward from the sun's surface, reaching into space for thousands of kilometers. And solar flares, a sharp increase in the sun's brightness and temperature.
Solar flares tend to happen over active regions, and active regions are essentially sunspot groups. So these are the locations where we definitely see the strongest flares.
So a reconnection event is essentially what produces the energy that causes both flares and CMEs.
Because the convective zone is very turbulent, many of the sort of current simulations show that most of the magnetic field as it rises through the convective zone is basically being destroyed, kind of being diffused around. It's more complicated magnetic structures, such like twisted magnetic fields that tend to survive. And so you can imagine, especially sort of over large sunspot groups, we do see very complex magnetic field configurations, magnetic fields, twisted, wreathed, basically creating these complicated geometrical topological structures. And it's within that structures that magnetic fields, the magnetic energy is stored. And what happens during reconnection? I tend to describe it, think of the magnetic field as a rubber band. So you twist it, turn it, and then basically at some point you pull it too strongly and it breaks. And that's essentially when we have the reconnection event. And what happens during the reconnection event? Essentially, as the name suggests, the magnetic field lines reconnect.
And when that happens, you get a lot of energy being released. Of the order of millions of nuclear weapons, nuclear bombs, all in one instant. And that energy will produce both solar flares, where large amounts of radiation is released, and also potentially lead to large-scale movement of the material that was suspended in the prominences, both towards the sun and away from the sun. When that reconnection event happens, then again, the material which is suspended in those magnetic fields normally will move one way or the other. A lot of it will move back towards the sun, often following those magnetic field lines, so moving to the footprints, like for instance, move to the sunspots, if that's where the footprints are. But equally, in the middle of those magnetic fields, quite often a bubble of material is essentially ejected away from the sun. And so what you'll end up having is millions of tons of charged material flying out from the sun relatively fast. Of the order of hundreds of kilometers per second to thousands of kilometers per second. And those are what we call CMEs, coronal mass ejections.
These CMEs come in contact with the planets all the time. Venus, when faced with a CME, has its lighter particles stripped away in the higher reaches of the atmosphere by the force of the ejection. This leaves the planet with just the heavier molecules, a toxic smog that cannot, as far as we know, sustain any life. Earth would have a similar fate if it wasn't for its relatively strong magnetic field. Particles from a CME aimed at Earth are redirected around the planet because of the Earth's magnetosphere. Some particles get redirected to the Earth's poles, where the charged particles hit the Earth's ionosphere, causing beautiful aurora. Thanks to a combination of the Earth's magnetosphere and atmosphere, we are totally protected from all sorts of particles space likes to throw around. Or are we? When the Earth is hit by a CME, this is called a geomagnetic or a solar storm. When a solar storm hits us, Earth's magnetic field gets somewhat compressed by the force of the CME for the duration of the storm. Normally this wouldn't and hasn't been a problem for people with their feet firmly on land. But what would happen if the most powerful solar storm ever recorded was to hit Earth today? To find out what is believed to be the most powerful CME in recorded history, we have to go back to 1859 to a solar storm known as the Carrington Event. From the 28th of August to the 2nd of September 1859, many sunspots appeared on the sun in one place. On the 29th of August, southern aurora were visible as far south as Queensland, Australia, which implies a solar storm was occurring. Before midday on the 1st of September, amateur astronomers Richard Carrington, who the event was named after, and Richard Hodgson separately saw and recorded an extremely bright solar flare. Carrington and Hodgson wrote reports independently, which were both later published in scientific journals. The flare was connected to a major coronal mass ejection that traveled directly towards Earth, taking 17.6 hours to make the 150 million kilometer journey, much faster than the speed of normal CMEs. Typically, a CME would take several days to reach Earth. It's thought that the high speed of this one was made possible by a prior CME, perhaps the cause of the large aurora event on the 29th of August in Australia, which would have cleared any ambient solar wind plasma for the Carrington event like a giant slipstream. With this slipstream in place, the way was set for the biggest CME known to man. On the 1st to the 2nd of September 1859, the largest recorded geomagnetic storm occurred. Aurora was seen around the world, all across the northern hemisphere, as far south as the Caribbean. The aurora over the Rocky Mountains in the US was so bright that the green glow woke local gold miners, who began making breakfast as they believed it was morning. It was reported that because the aurora was so bright, people in the northeastern United States could still read a newspaper. The aurora was visible as far from the poles as Sub-Saharan Africa, Mexico, Queensland, Cuba, Hawaii, and even at lower latitudes very close to the equator, such as in Colombia. This is unprecedented, as typically aurora aren't visible at the middle latitudes. By the 3rd of September, the aurora in the sky was said to be the brightest and most brilliant it had ever been. However, although beautiful, this storm brought unforeseen problems. A consequence of the geomagnetic storm was that the electrically charged particles from the sun surged telegraph systems all over Europe and North America, which caused them to fail, even in some cases giving the people that operated the telegraph equipment electric shocks. Telegraph pylons threw sparks from the charged atmosphere. Amazingly, some telegraph operators could still continue to send and receive messages even though they had disconnected their power supplies. The storm was comparable to a hemisphere-wide EMP bomb, fairly harmless to humans, but extremely bad for electronics. The force of the CME in 1859 was so strong that it compressed the magnetic field of Earth all the way down to its atmosphere. Due to the fact that North America and Europe were facing the sun at the time, these areas of the world were most affected from the initial cannonball of the CME. Looking back at geomagnetic storms since the 1850s, there have been a few which were big but not devastating. For example, in March 1989, a CME hit Earth, rendering satellites unusable for several hours and jamming radio stations in Europe. Power in Quebec was knocked out for about a day. Some people there incorrectly thought the Soviets were attacking, and the glow in the sky was the result of nuclear bombs. Thankfully though, this solar storm and many like it did no lasting permanent damage. Today, if a CME the size of the Carrington Event or bigger was to hit Earth, the consequences would be far more disastrous than they were for mankind in the 1800s. Technology was only just picking up back then, whereas today we have satellites in space, computers, telecommunications, power plants that would all be severely damaged in such an event. Due to the range of a solar storm, it would greatly impact equipment over a large area, the most susceptible technologies being the electricity grid and telecommunications, which have cables stretched out over a large distance. Without proper safeguards in place, transformers on the power grid could break, and millions upon millions would be without power for a lengthy period of time. If transformers did get damaged, for example, it would take years to replace, as transformers take years to manufacture. Often, these transformers are tailor-made for the specific requirement and are not mass-produced. Without power, refrigerators would not be able to stop food from spoiling, and as the transport system would also be down as fuel stations require electricity to pump, replacing that food would be problematic. Payment systems that rely on credit cards would not work. People would not have access to the internet as computers would not have power, and battery-powered devices would run out quickly. Radio and TV stations would be disrupted. Hospitals would struggle when the backup generators ran out of fuel. We would be completely cut off from the outside world. The world is simply so dependent on technology, and especially on electricity. It is feared we have lost the ability to function as a society without it. And worryingly, it is our power grid that is most vulnerable to a super solar storm. An independent think tank recently put the cost of damages to the USA alone at $2.6 trillion, ultimately destroying the economy. And unfortunately, that does not cover the social impact it would have. As is often the case in natural disasters, some people would undoubtedly resort to more primeval instincts, with attitudes such as every man for himself. Chaos, looting, and disregard for the law could occur. This would only get worse the longer the population goes without hearing from their government or organization of authority. Hopefully, in such a situation, the good of mankind would prevail, but it is a possible scenario. The think tank placed the estimated recovery time to repair the damage of a CME at 4 to 10 years, and estimated that 2/3 of the US population could die of starvation, disease, and chaos during that time. We only need to look at a couple of examples to understand the severity of the situation. In 1989, Quebec experienced a large solar storm that made the power grid fail in just 90 seconds. This problem was exacerbated by the fact it was winter, where the temperature can drop well into the minuses, which left vulnerable people in a potentially bad situation. It took 9 hours to restore power, and total costs from the disruption were estimated to be around 2 billion Canadian dollars. From the social aspect, we only need to look at Puerto Rico, which is still without power for 40% of its population from the time of writing this script in early February. That means it has been without power for 140 days, and is estimated that it still needs 50,000 utility poles and roughly 10,000 kilometers of electricity cables. If a solar storm hits, it wouldn't just be an island that is rendered powerless, it would be an entire hemisphere, and Earth has had some very near misses. A Carrington-size event could have been a reality in 2012, where a huge CME was ejected from the Sun. This was the biggest CME that has been recorded with modern technology, and it directly hit one of the stereo satellites that was observing solar activity. It is the charged particles that cause this distortion effect shortly after this solar flare. And had it hit Earth, the hypothetical disaster scenario could have become a reality. Due to lack of historical evidence, we have no way to predict when the next big CME could hit Earth. As far as we know, a CME even bigger than the Carrington event could hit us tomorrow, or the next one could be in a few thousand years. But what mitigation plans does the world have in case of such an event? Since 1995, NASA have placed a telescope in orbit which is constantly monitoring the Sun for CMEs. As light travels much faster than the speed of a CME, it would roughly give us about 17 hours warning before the CME hit Earth. If everyone was acting fast enough, this might be enough time to turn off some of the power stations, thus protecting the electricity grids. This is called the Solar Shield Program, and astonishingly, the US is currently the only country to have such a program in place. Countries are also working on temporary transformers which are quicker to produce. Additionally, countries throughout the Western world are currently in the process of proposing upgrades to the power grids that would not allow a surge of electricity caused by a geomagnetic storm to destroy the network. This process, however, is slow and bogged down by bureaucracy. It seems countries are in no rush to foot the bill to upgrade the infrastructure. These measures to protect the power grid are not already in place worldwide. It also seems that most people in the world are not even aware of CMEs, but rather fear much less likely scenarios like an asteroid hitting Earth or aliens invading. Mankind as a whole is shockingly unprepared for a natural disaster caused by a super solar storm. George H. Baker, Professor Emeritus from James Madison University, spoke before the House Committee on National Security in the United States and gave this explanation for the reason progress is not getting made. He said, "To a major extent, the lack of progress in protecting our most critical infrastructure to solar storms is that the responsibility is distributed. There is no single point of responsibility to develop and implement a national protection plan. Nobody is in charge. When I asked the North American Electrical Reliability Corporation about EMP protection, they informed me, "We don't do EMP, that's a Department of Defense problem." The Department of Defense tells me EMP protection of the civilian infrastructure is a DHS responsibility. DHS explained to me that the responsibility for the electric power protection is within DOE, since they are the designated sector-specific agency for the energy infrastructure. And this is sadly from one of the most progressive countries in the world on the subject. And until mankind is prepared for a CME, we really are at the mercy of our life-giver star.